Okay, this is the Bays Alberti Cook Group. We have implemented the Kakkot List, and this is an improved variation of the skip list. The Kakkot definition is as follows. It's an improved variation of skip list where instead of determining the height of each element by random chance, it is determined by the number of times the item has been searched. So quick review of skip list. A skip list is a third-dimensional linked list in which each of the elements in the list are randomly assigned a height. When they're inserted. When searching, the algorithm traverses through the list starting with the highest numbers, using them as an express lane to reach its target more quickly, so it goes through, drops down until it finds its target. The search time complexity for this algorithm is O log of n, because it's assumed that at each level there will be half the number of nodes. So some pros and cons of Kakkot List. Pros, it's very similar to skip list, so if you already have an implementation for skip list, then Kakkot List is really easy to switch to. Insertion and deletion are more efficient than in binary trees because there aren't any rotations or rebalancing required. It's all there. Cons are search time is linear in the beginning because it starts out as just a regular linked list. And it requires more memory than a binary search tree because it's a 2D linked list matrix. These are some Kakkot List operations as defined in the paper we used. So the create function creates the empty Kakkot list, is empty, takes the list as an input and checks if it's empty. Search takes the list and item as input and searches for the item and increases the height of the searched item so it's easier to access in the future. Insert takes the list and item as input and it finds where the item is supposed to go in the Kakkot list and inserts it with the height of 0. The delete and clear functions have not been fully implemented because they aren't completely necessary to the operation.
So we have the creation function, and this function essentially just initializes the head of the list. It initializes an empty list, and then then there's another class which creates each node, which has an up, down, right, and left pointer. Then we have the insertion function. This inserts a key at level 0. If the key is already there, the insertion function doesn't do anything. But if it doesn't exist within the list, it will always be inserted at level 0. Next, we're going to go over the skip list search algorithm. So the skip list search algorithm starts at the very top left of the list. It will scan forward until it can't scan forward anymore. And the way that it scans forward is it checks if the node to the right is less than the key that is being looked for. And if it doesn't meet those qualifications, then it will drop down, and it will continue this cycle until it finds the key that it's looking for. Now, to compare, we have the Kakkot List search algorithm. This search algorithm is the same as the skip list. It continues to do the scan forward and drop down cycle. However, whenever it does find the node that it's looking for, it will increase the level by 1 and then increase the height of that stack by 1. Now I'm going to go over the locality of reference. The Kakkot list is based on the locality of reference, so it assumes that if you search for a key more than you search for other keys, then that key and the keys around it are more likely to be searched. This is similar to splay trees. Next, we have the deletion algorithm. It's very similar to that of a skip list. It will delete the key that is put in as a parameter, and it will delete the key at every single level of the Kakkot list. And then finally, we have the clear function. To prevent an accumulation of an absurd number of levels due to repeated searches, the clear function was created. This function reduces the number of items in each level by 1/2. This serves to reduce both the time and space complexity of the search operation.
Now I'm going to give a quick demonstration of the Kakkot list. So first we test the isEmpty function, and it works. Then we add 1 to 9 to the Kakkot list, and these are each added to level 0. Then we search for element 8, and we see it is moved to the first level, up from level 0. Then if we do it again, it's added to level 2. And notice none of the other elements are changed. Then we search for 4, and it is added to the first level, and 8 still remains at the second level. Then we continue to do this, and then at the end, we see that 4 is searched for 2 more times. The first time, it is added to level 2, and then the third time, it is added to level 3.